The following presentation is a recording of the acceptance lecture given at the Robert H. Richards Award Ceremony at the 2023 SME Annual Conference, and it's entitled A Global and Mining Industry Perspective of the Role of Comminution in the 1.5 degrees C Future. The so-called 1.5 degree future came out of the Paris Climate Change Conference in 2016, where the agreement was made by heads of lots and lots of governments to try and limit global warming to 1.5 degrees compared to pre-industrial levels by reducing greenhouse gas emissions. Most, if not all, mining companies have formally supported this, and if you look at the websites of most mining companies, you will see that their intention is to reduce their greenhouse gas emissions by about 30 to 40% by 2030, 2035. And the baseline that they typically use to do that calculation is the 2018 to 2020 emissions levels. And what we're going to do in this lecture is have a look at what that implication is with respect to the amount of emissions that the mining industry is talking about and the extent to which comminution can help meet those targets. So, what are the baseline levels? Well, to help answer that, let's have a look at what the published literature says. And first of all, let's look at mining energy data. And I've chosen for you 4 sources of information. The first 2 are from government or government-funded sources. The third one is from a well-respected academic journal. And the fourth one is from a campaigning website. They all agree in that the mining industry appears to be a major consumer of energy in the global context. And the first 3 broadly agree to the extent that it's about 10% of world total energy consumption. And the fourth one goes as far as to say it's equivalent to as much as 80% of the world's electricity use. Let's look at published information on comminution energy consumption data. Once again, there are 4 sources. 2 from digital mining journals, which have a claimed combined readership of 64 million per year. Proceedings of a conference on life cycle engineering, which is cited time and time again in a number of papers. And the last one is from the Canadian government website. Once again, they all more or less agree on figures which suggest comminution is about 3 to 4% of electricity consumption, and that comminution is a very large chunk of the mining industry's total energy usage of the order of 50 to 56%. The Canadian government website doesn't provide any data, but it says in no uncertain terms it believes comminution to be one of the major energy consumers, and they have a government strategic plan which targets it. So my take on all of this is that the mining industry is a major player when it comes to emitters of global greenhouse gas to the tune of something like 8 to 11%. And that comminution accounts for well over the majority of those emissions, something of the order of about 50 to 55%. The inference I draw from that by simply multiplying those 2 sets of numbers together is that comminution in mining, therefore, accounts for something of the order of 4 to 6% of global energy and greenhouse gas emissions. And for those people, and many people don't know what comminution is, it gives rise to electricity consumption. And in that respect, it's equivalent to 3 to 4% of global electricity. And summing all of that together, once again, the inference appears to be that if we can significantly improve comminution energy efficiency in mining, we could have a very, very big impact on the global greenhouse gas emissions. Let's start looking at data, though before we do, we need to define the scope of our data collection and specifically what we mean by the mining industry. And I'm going to look initially at hard rock mining, which, if you're like me, if anybody says mining industry, I automatically tend to think of hard rock mining. And there's a definition of what the hard rock mining sector is. And it basically covers the sorts of commodities that I spend most of my life looking at in terms of mining problems and so on. And I think most of those up there will not be a surprise to you. In particular, that sort of top line of copper, gold, iron, lead, zinc, silver, nickel, and so on. So let's start off by estimating comminution energy. And remember, I'm taking 2019 as my base for these calculations. From the literature, I collected information on what the global annual tonnage is of each of the commodities in the hard rock mining industry. Let's call that C. Then from the same source, the literature, also augmented by discussions with experts of the industry, average ore grades and typical recoveries, called that G and R respectively. So the total estimated tonnes comminuted then, T, is simply C divided by G divided by R. Then I needed an estimate of the kilowatt hours per tonne for comminution. Let's call that E. The total amount of comminution energy then is simply the product of T and E. So now let's look at how we get E. I now need an estimate of the kilowatt hours per tonne used for comminution for each of those commodities. And I use the equation that the Global Mining Guidelines Group have adopted, at least one of them. That's called the Morrell equation, surprise, surprise. And that equation is given there. You don't need to be too worried about the detail of it, other than there's an MI, which is a hardness parameter. That's from the SMC test. I'll talk about that in a minute. And I need a P80 and an F80. Once again, I went to the database and literature to get typical F80s and P80s for comminution circuits adopted at each of those commodities. The hardness number, MI, I got from the SMC test or hardness database. And you can just see there on the left all of the different commodities that the SMC test has been done on. There's a total of just over 70,000 SMC tests that have been done in total. So for each one of those commodities, there's quite a few number of SMC tests. And on the right-hand side, they'll just give you some indication of the typical distributions of hardnesses that one sees. And I just chose a range of commodities there: tungsten, copper, uranium. So we were in a position to look at the mean hardness values, global values, for each of those commodities. And they do cover all of the hard rock mining commodities. So this is what we got in total. If you look at that figure at the bottom there, we estimated using that technique 140 terawatt hours per annum, specifically per annum being 2019. For those of you not too familiar with units, that 140 terawatt hours is 140 billion kilowatt hours per year for comminution and hard rock mining, and distributed amongst all those commodities on the left. And of note, the top three, copper, low-grade iron ore and gold, accounted for about 80%. So how does that figure of 140 terawatt hours compare to the total global electricity consumption? Well, that was 23,000 terawatt hours. So what this data says is that comminution accounted for 0.6% of global electricity consumption. And if you remember those earlier figures that claimed that comminution in mining accounted for 3 to 4%, that 0.6% can't be right. So I decided to do some reality checks, and this is the first one I did. And I went back to a really excellent study done back in 1981 called Comminution and Energy Consumption. It was funded by the USA Department of Energy and the Bureau of Mines and National Science Council. And they went back to some data that the Battelle Columbus laboratories generated back in 1975. And what the Battelle Columbus laboratories did was collect energy usage profiles from a whole range of commodities deemed to be important in the USA economy back in those days. And they gave their data in terms of the BTUs per tonne of final product. Nowadays that's called energy intensity. So final product might be, for example, tonnes of cathode copper produced. So it will be the number of BTUs per tonne of final copper. That's just an example. And they broke that all down into the various processes that went into feeding that, including comminution. And that 1981 study, which had all of the most well-known people in those days in the comminution world working on it, so a very authoritative document. They converted all those data into kilowatt hours per tonne for comminution of final product. They worked out for the 1978 was their base year, how many tonnes of those final products were produced in USA. They multiplied the two data together and they ended up with a comminution energy consumption for 1978. So what did that 1981 study conclude? Well, when I added up all the hard rock comminution data from that study, then in 1978 the conclusion was in the USA that comminution accounted for 0.44% of the USA's total electricity consumption, which now, looking at my original 0.6%, starts to suggest that perhaps 0.6% wasn't such a bad figure after all. Problem here, of course, is this is for 1978 and it is only applicable to the USA, not global, which was the figure that I was trying to get at, and of course a global figure for 2019. Reality check number 2 then was to take the hard rock comminution kilowatt hour per tonne data from that US 1981 study and just simply update it using global tonnages of each of those commodities for 2019. Bang on, as they say. I ended up with an absolutely almost identical figure to my original 0.6%. Maybe a bit lucky. I'm always a skeptic when I see numbers as close as that, so we'll look at reality check number 3. Ag, sag and ball mills absolutely dominate the comminution landscape of the hard rock mining sector. They are the really, really big energy users in comminution. And since 1996, the global installed capacity in terms of power of all ag, sag and ball mills in the hard rock mining industry have been available in the proceedings of the SAG conference, as we call it on the comminution side. SAG conferences have been held since 1996. They're held every 4 or so years. I went to the most recent proceedings and got the most up-to-date details of the total installed capacity of ag, sag and ball mills. I assumed a 90% utilisation of that installed power, 8,000 hours per annum of operation, and if you multiply the installed power by the utilisation and the number of hours per annum, you end up with an estimate of the number of kilowatt hours of electrical energy used by those machines. And what I ended up with is a figure of 0.5% of global electricity from those circuits in the hard rock mining industry. I've published all that information and the details of how I got those calculations in a paper last year in Minerals Engineering, and we'll have a look at that paper again in a few slides' time. I'm quite comfortable with that figure. It compares really well with our 0.6%, which is for all comminution, not just ag, sag and ball mills. And I think it's quite reasonable to assume then that that 0.1% includes crushers and circuits such as rod mill circuits, there are not many of those, and HPGR circuits that would not have been included in that 0.5%. So it looks like maybe our figure of 0.6% isn't a bad estimate after all. So where on earth does the 3 to 4% keep popping up? Where does it come from? The first thing, of course, is that the hard rock mining industry is not all of the mining industry. A broader definition would be hard rock plus non-metal valuables, coal, stone, aggregate, sand. That's what I would call the quarry industry. Clays, lime, pigment. There's a whole host of very, very small sort of boutique, if you like, mining commodities there. All those other, let's call them that, commodities added to hard rock would end up with, let's call it all mining as a category. What we find is that other mining adds an extra 105 terawatt hours to the original hard rock mining 140. And I should point out that 85% of that energy in other mining is just the quarry industry. It's absolutely dominated by the quarry industry. So our 0.6% for hard rock mining, to that we must add 0.5 now for other mining, giving us a total of 1.1% of global electricity. It's still nowhere near our 3 to 4%. So why the discrepancy still? Well, the first thing is comminution is the size reduction of solid materials. It's not just mining materials. And as it transpires, only 39% of comminution energy resides in the mining industry. If we look at global comminution, this is the breakdown that we get. There's our mining, all mining, at the top line there, 245 terawatt hours is 1.1% of global electricity and only 39% of total comminution. The reason for that is industries such as the cement industry, in terms of comminution energy, it is massive. Almost 50% of total comminution energy is in cement manufacture. Coal pulverizing, that's pulverizing coal for power stations and the steel industry. It's another very large percentage. Flour milling, believe it or not, that's rice flour, maize flour, wheat flour. Over 4% of total comminution is in flour milling. And there's a whole host of other small ones. And I've no doubt I haven't managed to find all of them. But in total, when you add them all up, you end up with comminution being 2.8% of global electricity consumption. Finally, we're not far off our 3 to 4% that's quoted in the literature. What about the claim then that comminution accounts for about 50 to 55% of the mining industry's energy consumption? If you dig deeply enough, you'll find that depending on the commodity, that figure varies actually from between 3 up to 45%. And if you use a weighted average based on the total contribution of energy of each of those commodities, a reasonable, I believe, weighted average would be it's about 35%. However, if you look at electricity, total electricity on a mine site, not just for comminution, then yes, you can get figures up to 60% of the mine's energy is electricity. And a reasonable weighted average there would be about 50% of mine's energy is electricity, and the other 50% almost exclusively is diesel, and that's for trucks and shovels. In the context of what we're interested in, which is greenhouse gas emissions, the amount of electricity consumed by comminution is not in itself important. It's the greenhouse gases that are emitted from the generation of that electricity. To get that figure is really easy. 2019 published figures which say how much CO2 tonnes per terawatt hour was used globally. So we simply need to multiply our terawatt hours by that figure, which is 556,000 tonnes. For the hard rock mining industry then, comminution, greenhouse gas emissions, and that's based on that 140 terawatt hours that we obtained in an earlier slide. When you convert that to greenhouse gas emissions, you end up with 78 million. The global emissions were 50 billion. So hard rock mines, comminution, accounted for 0.16% of global greenhouse emissions in 2019. However, remembering what we did before, hard rock mining is not all mining. So let's look at all mining in a similar manner. And when we do that, we find that 0.16% now inflates to a total of 0.27%. Now remember that very, very early slide, the published consensus, the inference was that comminution in mining accounts for 4 to 6% of global energy stroke CO2 emissions. 0.27% is nothing like that. What about the total emissions from mining? We've just been concentrating on the comminution component. So how do we get the total emissions from the mining industry using all those previous numbers that we've looked at? Well, we've got the CO2 from burning fossil fuels used for electricity supply. Those are the figures we've just looked at. And we've come to the conclusion that 35% of mining energy is from comminution. So we know we can calculate the other 15% because a total of 50% comes from electricity. So we can get that figure. And the remaining 50% is diesel. And there are tables which tell us how much CO2 comes from burning diesel. So we can get the total emissions from the mining industry via the comminution data. Looking at hard rock mining first, what we find is the total emissions, greenhouse gas emissions from the hard rock mining industry using that calculation route ends up by being 0.28% of global emissions. And when we look at all mining, not just hard rock mining, the figure we get is that total emissions from that sector accounts for 0.49% of global emissions. Once again, remember the published consensus that we looked at right at the very beginning of this lecture was that the mining industry consumes about 8 to 11% of global energy or CO2 emissions. So where do data in published literature which give comments like the mining industry consumes 8 to 11% of global energy or CO2 emissions come from when my calculations can't even get to 0.5%? I don't know for certain, but there are two possible reasons. The first of which is that many papers in this subject area or reports will headline mining industry. But as soon as you get in the text, you realise they've included the metal smelting and refining industries in their data, and sometimes even the oil and gas industry. So in other words, they've defined mining industry as including all of those other industries. And the metal smelting and refining is huge when it comes to energy consumption. It's 8% of global GHG emissions. and that is absolutely dominated by the steel industry. So on that basis of definition, if we add our 0.5% to that 8%, we get 8.5%. The second possible reason is related to what those percentage figures use as their baseline. Global greenhouse gas emissions are about 50 billion tonnes of CO2. Global energy-related emissions, and that excludes agricultural waste treatment chemicals, are about 35 billion tonnes. Now, the latter value is quite often used as the basis for calculation, and that inflates the percentage by over 40% compared to using the global greenhouse gas emissions. And I have a sneaking suspicion that is done more often than not. So on that basis, our previous 8%, which I calculated on the basis of that 50 billion tonnes, climbs now to 11.5% if I use the global energy related value of 35 billion. And so our mining industry, with our new definition, value climbs to 12%. Well, let's not get hung up on just how much comminution and the mining industry accounts for on a global scale. We'll go back to that right at the very end in a couple of slides' time. Let's just look at our own industry. Look at comminution. We certainly accept the fact that comminution is a large chunk of the mining industry's energy and therefore greenhouse gas emissions. What can we reduce it by in the foreseeable future? And the targets are almost exclusively ag, sag and ball mills. They're the big comminution energy users, and they are almost exclusively in the hard rock mining industry. If you look at the other mining that we talked about, which is mostly quarrying, they already use mostly reciprocating type crushers, and they are very efficient machines in the first instance. There is nothing, in my view, on the horizon that's going to replace those. But within the ag, sag and ball mill sector, there is no doubt in my mind that HPGR technology is the most viable candidate for significant reductions in energy. And that's going to remain the same, I suspect, for at least the next 50 years. You might think that's a long time, but Schernit's first patent for HPGRs was 1977. And look where we are with HPGRs. We're only really just beginning to introduce it. And there's no technology that I know of, even in the pipeline, that is going to come to the fore. And even if it did tomorrow, on the way our industry operates, it is not going to get into use for at least another 30 years. That's just how we are. Now, the good thing about HPGRs is that they really are very easy, relatively easy, to size and to predict their performance at the design stage. So in terms of future circuits, very, very easy to size them and evaluate them. And certainly in terms of replacing the existing ag and sag mills, not too difficult at all. And the paper I mentioned earlier, I published last year, goes through in detail how you can accurately size and predict the HPGR performance. Don't let anybody tell you that HPGRs are complicated. They are not. They are so much simpler than ag, sag and ball mills. And there's no reason at all why those devices can't easily be incorporated into the comminution circuits of the future or retrofitted. Let's say we could wave a magic wand and replace all of the current ag sag mills that are operating with HPGR technology. Then about 16 million tonnes per year of CO2 could be saved. And that equates to about 20% of the hard rock mining comminution emissions. And that figure, that calculated figure, is easily borne out by the energy savings that have already been published and confirmed at operations like Cerro Verde, Boddington, Morenzi, Tropicana, and there's a couple of others. What happens if we could also replace ball mills with HPGR technology in those circuits? Then we'd end up with approximately, and these are very, very round figures, we would end up by saving a total of 32 million tonnes per year of greenhouse gas emissions, and that would account for a saving of comminution emissions in hard rock mining of about 40%. You might think that replacing the ball mills with HPGRs in ag-sag mill circuits is a bit way out. Well, think again, because Fortesque Metals' Iron Bridge Magnetite plant, I believe it's already delivered its first concentrate, has that circuit up and running as we speak. And they put together, I think it was a $500 million pilot plant to test all of the technology they have in this circuit. And they've confirmed that HPGRs in an equivalent of an ag-sag roll and then subsequently in the ball mill roll saves between 30 and 40% of energy. So definitely viable, definitely proven. So let's get to conclusions. And conclusions number one, the mining industry, if we define it as uncovering and extracting metal and non-metal mineral deposits, accounts for 0.49, 0.5% of global greenhouse gas emissions. And that's based on 2019 data and not as the widely published figure of between 8 and 11%. Conclusions number two, comminution in this case. If we look at the global electricity consumption, then across all industries, not just mining, it accounts for just under 3%. In the mining sector, it accounts for just over 1%. And if we look at just the hard rock mining sector, it accounts for just over 0.5%. Number three, HPGR technology really, in the next 50 years, as far as I can see, is the only viable technology that can significantly reduce the mining industry's comminution greenhouse gas emissions. At best, it could reduce those emissions by 32 million tonnes per year, but only if it were to replace all existing ag, sag and ball mills in that sector. The technology, however, is readily and easily installable. Last conclusions, conclusions number four. If we look at that maximum HPGR saving of 32 million tonnes per annum of greenhouse gas emissions, if you look at just the hard rock mining sector, it has the potential to reduce their emissions by 23%. If you look at what we've defined as the all mining sector, this is equivalent to 13% of their emissions. In the global context, it is equivalent to only 0.06%. Do the mining industry and the comminution process in the mining industry significantly contribute to global warming via the greenhouse gases emissions that they produce? I don't know. I'm not qualified to answer that, and I will leave that decision, that conclusion, for you to make. I do believe, however, that within the mining industry, we should make every effort we possibly can to reduce our greenhouse gas emissions, and in that respect, within the comminution sector, HPGR technology does have the potential to significantly reduce our greenhouse gas emissions. Thank you.